Hello, everyone. In this video, I'm going to go over the common fate moderation model. And in this example, we are going to use maximum likelihood. And so there are three different ways in which that we can test interactions using dyad level processes. And I'm going to go over the one, again, with maximum likelihood in this video. In other videos, I go over alternative methods using Bayesian estimation as well as the product indicator approach. So this video is associated with the article entitled Estimating Diet Level Processes in MFT Research, General Overviews of the Common Fate Model and Extensions into Mediation, Moderation, Growth, and Hybrid Models, again, published in a Journal of Marital and Family Therapy. So let's go ahead and let's jump into the M plus syntax. All right. So there's going to be several steps in estimating the latent interactions in the common fate model. Um, and the first thing that we are going to do is we're actually going to estimate the model without our interaction term in the model. So one of the things that we're going to be doing using this maximum likelihood method with latent moderated structural equations is that we're actually not going to obtain traditional model data fit indices. So our CFI or TLI or RMSCA or SRMR, those are not going to be available in our output. So one of the things that we want to do is we want to estimate our model without that interaction term, establish that we have a good fitting model, and then we're going to make the assumption that we can, by adding in that one interaction term, that one extra variable into our model, that's not going to significantly harm model data fit. All right, so by adding in this extra parameter, it's not going to adversely affect the model data fit. Perhaps if it's non-significant, we're more in danger of overfitting and obscuring the interpretations of other variables than anything else. But we're, again, not assuming that that we're going to harm the data to the extent where we now have a bad fitting model. All right. And so, again, if you're new to M plus or you're new to this series, in the first video where I go over the common fate model, just like that baseline common fate model, I talk more in depth about the variables and things like that and an introduction to M plus. So if you are, again, kind of lost with what's here, then I would check that video out first and then return to this one once that is making more sense. So what we're going to do is we're going to test the mediation model, and we'll scroll down down, and we'll start with this use variables command. And so we're going to have dyadic coping, common dyadic coping of the dyadic coping inventory, that subscale, is going to be the mediator between relationship mindfulness for men and women and relationship quality for men and women. So we have three common fate latent variables here, and all of these variables theoretically occur at the dyadic level, right? And so you'll see here I've actually removed two participants because they clicked through the survey, so they have all fours, and so we obviously don't want that invalid data in our survey. And this is the M plus syntax in order to get rid of them. So we're using all observations. That's what we're going to assume, and then we have dyad ID, and so we need that dyad ID variable up there is not equal to, and then this is the couple ID number, and separates out removal of each dyad. All right, so what I'm doing here is I'm removing the whole dyad from the analysis. I'm not just removing one partner. All right, so we are going to use a robust maximum likelihood, but we can also use bootstrapping. Bootstrapping tends to be the preferred method of testing mediation, but one alternative is, again, robust maximum likelihood, which you will actually have to use in certain applications where bootstrapping is not available. Typically, that's in multi-level SEM with dyadic data, but certainly we could certainly do bootstrapping here. Right. And so we're first going to establish the measurement model. So what the measurement model is, and it happens to be our final model in this case, is we're going to create those latent variables, those common fate latent variables, where we are going to create our latent variable and use the by statement to specify factor loadings, and then we're going to fix the male and the female partners reports of that dyad level process to be one. So we create kind of a mean or an average between the two dyad members, and everything that differs between the dyads actually going to go into those residuals of these variables right here. Right. And then we're going to do that for each variable. So we have relationship quality, measure the dyad level with factor loadings fixed to 1. And then we also have relationship mindfulness with factors fixed to 1. Right. And so what we're going to do here is specify the regression coefficients. All right. So on statements and then plus are those regression coefficients. So we have CSI dyad on relationship mindfulness. Actually, I need to add in that beta path that I had accidentally deleted. So this is going to be our C prime path. All right, if you're familiar with mediation terminology, this is the regression coefficient of the IV and the DV when the mediator is present. And when you don't have the mediator, that's just called C path, right? And then we have our effect from our mediator to our dependent variable and our independent variable to our mediator. And order here does not matter. Okay, so it's whatever really works for you. And plus, it doesn't really require you to code things, left to right as we create as we normally would in our figures. Right? And then what we're going to have here is, as in we normally would within the common fate model, are those residual within person covariances. So we're correlating the errors of males' reports of relationship quality and relationship mindfulness, for example. And we're doing that for all possible within person or within dyad member residual covariances, right? And so what we can do now is actually just go ahead and we can run this, right? And we will have, if we've specified our model correctly, 3 degrees of freedom, all right? And here's where we're going to evaluate model data fit. All right, so we have 3 degrees of freedom. Our chi-square is 6.96. Our scaling correction factor is 1.06. If the values of this are below 1.05 as a general guideline, a general rule, generally that scaling correction factor is not needed. So we actually may even be able to kind of just remove the scaling correction factor, remove the robust the part of this, and just use regular maximum likelihood. Because essentially this is telling us that our errors are actually pretty close to normally distributed, right? And so that would actually make bootstrapping actually a pretty solid option here rather than robust maximum likelihood, because we don't have to worry about those non-normality of the residuals, but we do have to worry about the non-normality of those indirect effects, which bootstrapping does a really good job at addressing, right? So we'll scroll down to the RMSEA. We can kind of ignore the RMSEA in this example. The RMSEA performs really quite poorly when there are few degrees of freedom in the model. And so generally when there's less than 10, but even less than 15, the RMSEA is actually biased. So the more and more degrees of freedom that you have, the more and more weight you should put on the RMSEA. There's a great study in 2015 by Dave Kenny that talks about the RMSE's performance at various sample sizes and model degree of freedom. All right. And so you can even actually go take a look at that. Just go in the RMSEA formula, just go and plug in different degrees of freedom at different sample sizes, and you'll see that the RMSEA fluctuates really quite considerably. Right? So it fits okay. Generally, 0.05, 0.06, 0.08, depending on who you are. So our MSE isn't terrible. So, we'll use it as a piece of information, but I'm going to place more weight on the CFI and the TLI because they tend to, again, do a little bit better in those smaller sample sizes compared to the RMSEA. But all in all, our model is actually doing really quite well. So I'm happy enough with our model data fit. And so this allows me to feel comfortable enough to move on to testing the latent interactions. So one other thing that we'll want to take note of here is going to be this H null value or H naught value. So this is going to be our -2 log likelihood. So this is a fit index, much like the CFI, the TLI. But it really, we don't really know whether the value, the negative, 4804, is high, is it low? We do know as values approach zero, they get better and better and better. It indicates better and better fit. But, is this a really small value compared to what it could be? Is this a really big value compared to what it could be? We don't really know. So that's kind of the problem with this statistic, is that it doesn't tell us what's good is good. And if you're a multi-level modeler, you've probably run into some of these problems in multi-level models. Because one of the benefits of SEM is that we actually say we have a good fitting model. Um, but what we will use this for, and what the negative two log likelihood is actually really good for, is comparing nested models, or models that are nested within one another, where you're just making subtle changes. And that's actually what we're going to be doing when testing the common fate moderation model. We're going to be inserting one new variable, that interaction term, and then we're going to be estimating only one additional pathway, the interaction term predicting the dependent variable. And then we're going to do a likelihood ratio test where we're going to compare the negative two log likelihood value of this model compared to the model with the latent interaction in it. And we're going to see whether or not there's a significant difference, right? So that's why we actually need, another reason why we need to run this main effect model first. We need to obtain this value, and we need to check out all of these fit indices, right? So what we're going to do next is we're going to move into the actually testing the moderation, the interaction effect. Right, so we'll start at the analysis command. So everything else above here is identical to what was discussed in the main effect only model. But in the analysis model, that's where we are going to be making changes, right? And so the estimator stays the same, but we need to use the integration algorithm. So when we test latent interactions, there's no closed form solution. And so what we're going to need to do is use the integration algorithm to estimate the values of the latent variables. So the integration algorithm is actually very computationally intensive. M plus is exceptionally quick. So it likely won't take all that long, but if you have an older computer or you're working remotely, this analysis probably can take a decent amount of time, several minutes for models to converge, right? And then we also need to add in type equals random, which is also required for latent moderated structural equations, right? And so what we're going to do here is estimate the common fate variables like we would in the main effect model or in other models where we're testing the interactions. So that doesn't change. But what we're doing here is kind of what's different. So when we're used to testing moderation, we're used to creating an interaction term by multiplying the level, the IV times the moderator, and we enter that into the model. And if you're familiar with M+, you generally do that here in the define command. So if we were using traditional moderation analyses, it would look like, the interaction equals dyadic coping times relationship mindfulness. That's how we're taught to do it in multiple regression within the general linear model with observed variables. But one of the things that we're doing here is we're multiplying latent variables together. So in M+, we actually don't do it this way. In M+, we are actually going to specify the latent interaction term here. So I am calling it int. Right? You can use any name that you want, knowing full well that M+ can only read the first 8 characters. And then you use a vertical pipe, and then you're going to specify what latent variables you want multiplied with one another. And then you're going to use X width. So the X width command is actually telling M plus that we are testing latent interaction. All right. So again, this is the one line of syntax create does all of the work for you in M plus. And then here you will see that we have the regression coefficients, the kind of the structural portion of the model. And you will also see that I have actually parameter labels on them. And that is because I will be testing simple slopes. So simple slopes is a way of kind of probing the interaction term to see what is the slope of the IV on the DV at varying levels of the moderator, and is it significant or is it not significant? Because the interaction term it's interpreted um, as like a 1 unit increase in the levels of the moderating variable leads to gamma unit increase or decrease in the effect of the IV on the DV. So that's how it's interpreted, right? But interaction terms, for those of you who've worked with them, they can get kind of tricky, right? And so with that interaction, with that interpretation, it gives you kind of a general sense of what's happening, but you don't know at what levels the slope of the IV becomes significant or non-significant or shifts of the moderator. You just know that it is significant. And really what that is telling you is just the amount of variance that is explained in the model. All right. And so again, that's what we're going to do here. Is we're going to provide us a nuanced way of understanding at what values of common dyadic coping is relationship mindfulness associated with relationship quality, right? And so what we're going to do is go down to the model constraint to estimate these simple slopes. Right? So I'm actually going to go back to the main effect only model. And I'm actually going to scroll further down. Actually, I'll go up first. And you'll notice I have requested the Tech 4 output. All right. And so that gives you all the way down here your latent variable matrices. All right. So you have Tech 1 here, which is just labeling your parameters. And then you have your starting values. And then you have your Tech 4 output here. And you'll notice that the means of all the latent variables are 0. So they're essentially that's a default by M plus. We're going to fix that latent mean of the common dyadic coping um, variable to be, again, 0. All right. Um, and you have your estimated covariance matrix for your latent variables, which this is actually what we need. So because the means are going to be fixed to 0, what we're actually going to do is we want to obtain the variance of our variables, and we're actually going to use that to obtain the standard deviation so we can create the simple slopes. So when we're testing simple slopes, we traditionally use the mean, which in our case is actually going to be 0. And then we're going to do plus and minus 1 standard deviations typical. I actually like plus or minus 2 or even 3 standard deviations because once you're at plus 3 standard deviations, you get around like 99.7% of the distribution. When you're at plus or minus 2 standard deviations, you're at 95 or 96%. So you're capturing a pretty full range of the distribution. And so, again, I like a little bit more nuance in that. So, what we're actually going to do is use these variances to obtain the standard deviation. All right. And then one thing I actually had forgotten to mention before is we'll also want to run the main effect only model because we want to understand how much variance is being accounted for by the model without the interaction term. So then we can subtract the variance accounted for in the model with the interaction term, and then we can obtain how much of the variance that the moderator or the interaction term is actually accounting for. All right, so that's another reason, and that's why you want standardized output, the STDYX. All right. All right. So just take note of this of 64.6. Right. And so what we're going to do is we're going to have actually, I may have misspoke earlier, we're actually going to have relationship mindfulness serve as the moderator of common dyadic coping and relationship quality. It actually doesn't matter because multiplication, it doesn't matter which term comes first. Multiplication and addition, you can flip them and it doesn't change anything. It just might mean something theoretically, right? But for us, we're more focused on the statistics behind it. So we are actually going to test relationship mindfulness as the moderator. And so if you recall, I had 11.87. I got that from the Tech 4 output. So that means the standard deviation is 3.44 because I took the square root of this variance to obtain the standard deviation. And then I created these simple slopes. So the V high mod is going to be 2 times 3.44. And then we have 3.44. And then you can see kind of where this is going, where we have two plus and minus 2 standard deviations above the mean. We have the mean, and then we have it below the mean, right? So in the model constraint command, we actually have to create each of these new parameters. So we are inserting this into the model. And so we use the new command, and then the parentheses um, are include the new variables that we are creating. So you'll notice these labels that I've highlighted are identical to these labels right here. All right. And so it's just me telling M plus for this variable, I am assigning this value, for this variable, this value, and so on and so on and so on. And then we'll see we do that again here, down here when we're creating the actual simple slopes equations. Okay. And so moving down to the simple slopes equations, we have very high. So this is going to be the effect, our main effect, all right? And then this is going to be plus, and then this is the slope of the moderator, all right? So again, and then we have our V high mod. So the slope of the moderator times this specific value of the moderator. All right. And then that's going to be the effect that we see when it's very high. All right. And then we're going to do that at high and at med and at low and at very low. All right. So again, we're just adding in the slopes plus the slope of the interaction term at very specific levels, and then we're seeing what the effect on relationship quality is. All right. And so we can actually disregard all of this down here. That's supplementary. And so we can actually go ahead and we can run this. So again, this is the Monte Carlo integration algorithm. And so we'll scroll down and you'll see our fit statistics are pretty much gone. Okay, right? So we have our log likelihood value, right? So we'll need that. And then we have our model results, right? And so there's a couple of things that we can do here. And to me, it doesn't really matter on the order, but I'll look at the significance first. So we do have a significant interaction, all right? And so I'll scroll down to the variance accounted for. And so it accounts for, 82.8. So that means in this analysis, the interaction term is roughly accounting for 18% of the variance in CSI dyad. So before it was something like 64.6, and now it's 82.8. So we have a fairly substantial interaction effect. And so, from the significance test, where the slope of the interaction term is significant, one of the things that we can kind of assume is that the model, at the addition of that interaction term, is good for the model. It's increasing that model data fit, making it better. So those -2 log likelihood values are closer to 0. But one of the things that we will want to do is actually statistically compare them. And so I actually use R for that. M plus has a chi-square difference test, but is only for specific estimators such as like WLSMV, which is often used in like categorical data analysis. So what I will actually do is use the SBS diff test package, SBS diff, in R. And so I will load this package. All right. And this essentially provides a chi-square difference test accounting for the scaling correction factor. All right. So remember that scaling correction factor is used to address non-normality in the residuals, and it specifically addresses the kurtosis in those residuals. right? And so that provides a modified chi-square value, and your standard errors are different, all right? So oftentimes your standard errors are actually going to be higher, and they're actually going to be more accurate because when we have the non-normality in the residuals, that can actually lead more often to a type 1 error compared to a type 2 error. So what we're going to do in the SBS diff test package is we are going to first enter in the -2 log likelihood from our model with our baseline model. All right. This is be our first model, and then we're going to add in the model from the model with the latent interaction. So here this will be the main effect only model, and then this will be the um, interaction model. And then here, P0 represents parameters, right? And P1 represents parameters in the interaction model. So we are estimating 24 parameters in the main effect only model, right? And so actually I can show you an M plus where you get that. And that's model fit information, number of free parameters, right? So 25. So that means we were just looking at the interaction model, right? So in latent interactions with LMS, you are only estimating one additional pathway, and it's the effect from the latent interaction to the dependent variable. Unlike other moderation analyses where you covary the IV and the moderator with the interaction term, when you use latent structural moderated equations, you do not do that, okay? And then here we add in the scaling correction factors for the respective models. And so our first model has a scaling correction factor of 1.06. And then we had a scaling correction factor of 1.34 in the first model. And then what we're going to do is just type in SBS log.log. And this, I'm telling the package, I want you to estimate a difference that's based on the -2 log likelihood values. You can also use like the chi-square test. This is also, perfectly amenable to that. And then I'm just listing out these parameters that I have listed here. All right. So essentially, this package is just entering in information that you get from the M plus output. And we'll go ahead and enter that in. And so what we have here is a significant test. So this means that adding in the interaction actually significantly increases the model data fit, right? So our model data fit went from 4,800 to 4,789. And again, values closer to zero are better. So that means this has the better fit because again, it's a negative value and it is significant, right? So you should get congruent findings here from the p-values of the slope and the likelihood ratio test, although you might get some small discrepancies, particularly when p equals 0.049 or something like that. But for the most part, they are going to be fairly consistent with one another, right? And so the recommended way of actually doing this is actually not to use the robust method. What Maslowski and colleagues in 2015, what they argue is actually to run maximum likelihood for these nested models. And then once you have your final model, that's when you go in there and you throw robust in there. And so I'm actually going to show you how to do that as well. And this is where we're going to do the maximum likelihood difference test. All right. And so we will have to rerun the models with just maximum likelihood. So we'll remove MLR. So it'll just be, estimator equals ML in M plus. So it will look something like this, right? So it'll look like that. So just estimator equals ML. And this is by default. So you can actually even delete that line if you so choose. Right? And so this is the maximum likelihood, the log likelihood value from the maximum likelihood model. And this is the one with the interaction in it. So this is main effect only. And then this will be interaction model. Number of free parameters does not change. And the scaling correction factor we're actually going to set to 1. This is actually going to be the default, and this means that the residuals are normally distributed. And so when we're actually calculating this log likelihood difference value, um, we're actually again accounting for that scaling correction factor. But if there is no scaling correction factor, such as when it's 1, then we're just going to get a traditional chi-square difference test. M plus actually it doesn't allow you to do those difference tests with maximum likelihood or robust maximum likelihood, to the best of my knowledge. So I either use an online chi-square difference test calculator. Those can be kind of hit and miss because some of them are analyzing like count data, and we need one for structural equation modeling. So what I do now most often is I just use this and just set these scaling correction factors to be 1. All right, so we can go ahead and we can run that. And you'll see without the scaling correction factor, we are extremely significant, right? And so we have p is less than 0.00000000438. That was 8 zeros, right? And we have, again, 1 delta degree of freedom, and then this is how much our -2 log likelihood increases by in this example, because again, value is closer to 0. And so both tests should give you the same answer. But again, so in my experience, it doesn't much matter. Often, which test you use, whether it's robust or whether it's with traditional maximum likelihood. But I run both just to be sure. But if there's any incongruence, I will rely on the maximum likelihood difference test. Again, incongruence with Maslowski and colleagues. Right? So that is how you empirically test the log likelihood difference test, or the chi-square difference test, or the log likelihood chi-square difference test, using R, specifically this SBS diff package. Right? And then so we're going to again specify everything else is just the same. And actually, I'll need to rerun it. We'll scroll down. All right. So again, the interpretation of the interaction effect is, a 1 unit increase in common dyadic coping leads to a 0.130 unit decrease in the slope of relationship mindfulness on relationship quality. So as dyadic coping gets higher and higher and higher and higher, so as couples do more and more and more shared dyadic coping, common dyadic coping, the beneficial effect, I'll even say, of relationship mindfulness decreases on relationship quality. All right. And then we'll scroll down some more. And then under the new and additional parameters is going to be our simple slopes test. And so you can ignore these first 5 since these are constants, right? So scroll back up to the syntax. That's these guys right here. And I fixed them to be a very specific value. So we can kind of disregard them. Those can go away, right? These are a test for simple slopes, right? So these slopes are significant. So our p-value is less than 0.05. And if we want to scroll down and we want to report our confidence intervals, those will be right here, right? So we have our point estimate right here, and then we have our 90%, 95%, and 99% confidence interval. And this tends to be what I report in my studies. Since we're not using bootstrap or anything like that. These are going to be, I think either identical. They're going to be extremely close or even identical. I think they may even be identical with the p-values associated with up here that we use to evaluate significance. All right. But again, I prefer confidence intervals because they tell us more information about the precision, they provide more information about the standard errors by seeing the spread, the distance between our upper and our lower bound. That gives me a little bit more information than just telling what the standard error actually is. Again, I do prefer confidence intervals, but in this circumstance, they will not give you any different results. That will change when we talk about bootstrapping for mediation. You will get asymmetric confidence intervals, and you would want to interpret these confidence intervals, and you would not interpret the p-values, right? So hopefully this has been helpful. There's another way to test moderation, and that's going to be using Bayesian estimation. And then that's also going to be also introduce the idea of Johnson-Neyman output, and specifically Johnson-Neyman plots, which is where they're often called butterfly plots, is where we can actually visually represent the data and we can identify the exact values of the moderator where the slope shifts from significant or non-significant to significant or to non-significant or significant. So it's an even more precise way to understand where the significance actually is. And I think that can actually lead to more precise, perhaps clinical utility if we administer the same skills that are done in research studies, that we can know those precise values at which we may want to do something a little bit different as a clinician, as a marriage and family therapist. Right? So hopefully this video has been helpful in introducing you to the idea of latent moderated structural equations, to the common fate moderation model, to simple slopes, and how you would, again, estimate these models. Thanks for stopping by, and I appreciate you watching.